warm good evening to everyone present here. So, just a quick note before I begin this session. So, like, if you have any queries or if you have any doubts or questions, I request all of you to please put it in the chat box. We will not be pausing the webinar in between anytime because this will be like this will be continuously done. And once the webinar is completed, at the end, we will spare like 10 to 15 minutes for some question and answers. So please again leave all your questions in the chat box, and we will address them at the end of the session. Yeah. So with that, we will begin with today's webinar content, that is open circuit voltage characteristics of a lithium-ion cell. My name is Abhinav, and I work as a BMS algorithm development engineer at Decibels Lab. So I work on developing equivalent circuit models for cells, lithium-ion cells, lithium-ion battery modules, and battery packs. And we focus entirely on simulating them, validating them, and verifying their performance and behavior in different situations. So apart from that, I'm also involved in developing battery management system algorithms like uh, state of charge, state of health, internal resistance estimation, temperature estimation, and things like cell balancing, all these things, and also involved in testing them in real time using like some NXP microcontrollers and things like that. So I'm also involved in like cell level and battery pack level testing as well. So where we subject the cells and battery packs to different loading and unloading cycles. So especially at elevated temperatures or at very low temperatures, how do they behave? So that is one of my roles that I perform at Decibels. So today we'll be focusing on some some of the important and interesting characteristics of a lithium-ion cell pertaining to its open circuit voltage behavior. So let me show what we are covering today as a part of this webinar. So we start with first defining what is meant by open circuit voltage. So first, how do we understand what is OCV or open circuit voltage of a lithium-ion cell or any electrochemical cell, any energy storage device? Then we will touch upon the factors which we have to consider while we measure the OCV of a lithium ion cell. So, what are the influencing factors? What can cause the OCV to deviate, or what can cause it to undergo some changes, or change in the trend lines? All these things. Then we come to understanding the methods of testing and measuring the OCV-SOC curve. So there will be like some graphical analysis done over here. So you will be able to understand what are the two different methods of testing, two or three. There are few methods are there. So we'll be touching those, and then we will have uh, a quick overview of what is meant by accuracy of the OCV curve. So what, or how do we define accuracy? And after this, we'll have a short hands-on. So there is an Excel file that I have with me. I will provide this at the end of the session, and you can like just take a look into that and see some data that has been given there, and then you can go for like some quick hands-on and come to some conclusions. So after this, we come to the applications of the OCV-SOC curve. So where all they are used in some applications like BMS, algorithm development, or modeling and simulation, things like that. Okay. So before we begin with this webinar, there's a quick poll, set of poll questions that I'd like to hand over to the audience. Like, so ma'am, I suppose you can share the set of first poll questions, and requesting all the participants to please fill this out. And yeah, and then we can proceed further. Yeah, so we can just have a quick discussion on what are the possible answers, and then slowly as we proceed through the webinar, we can understand slowly what is the implications of each question that has been put across here. So what is the correct definition of OCV, open circuit voltage of a lithium ion cell? So there are two answers which may look possible to this. One is that it is the voltage of the cell measured immediately after the load is disconnected. And I see that around 37% of the people have answered that. And there is also another answer. It is the voltage of a cell measured when it achieves near steady state condition after the load is removed. And I see that 45% have answered that. So the correct answer to understanding the definition of OCV is answer number three. It is the voltage of a cell measured when it achieves near steady state condition after the load is removed. So we'll understand this with an example. So like I'll be presenting a simple example in the next few slides. And then using that, we'll be able to understand what exactly is the definition of OCV and why is it that we say it has to be measured near steady state. We'll see that. And then we come to the second one. Is the OCV of a lithium ion cell sensitive to temperature? So yes, it is very strongly influenced by temperature. So we will see that. We will see that with again another example as we proceed. Then does the OCV of a lithium ion cell change with the age of the cell? So again, here age does have some influence onto the OCV behavior, the OCV pattern. So again, in the future slides, we will see exactly how that happens. And then what are some of the applications of OCV? So it's all of the above. Basically, OCV is utilized in pretty much everything that we see in terms of battery pack applications, like resistance measurement, SOH, uh, in terms of temperature, in terms of SOE, SOC, everything. So yes, with that we will be proceeding forward. So let's start with the definition of open circuit voltage. So basically, it is defined for any electrochemical cell. It is defined as the voltage of the cell that is measured when it is in a fully relaxed, or you can also say fully rested condition. So when we say fully rested or fully relaxed, it means that the voltage being measured has very less variation. And sometimes that can also have a number like 4 microvolts per second, or maybe something like 10 microvolts per second. So it depends upon the application there. So usually for electric vehicles and sensitive battery management system applications, you will define OCV to be having a value which is very small. That is less than 4 microvolts per second. The variation is very small. Okay. So we define open circuit voltage as the voltage of the cell which is measured when it is in a fully rested or a relaxed condition. Okay. So further about this, we will see regarding cell testing, a little bit is covered regarding that. So we will see that when we come to that particular portion. So how exactly the testing is done to understand this, we will see with some examples. All right. So proceeding forward to understanding further on OCV or open circuit voltage. So let's take a case. So in here it's called case one, where the cell voltage is observed during load and during no load. Okay. So the regions have been clearly shown here. So the red box represents where the load is turned on or the load is switched on, and the cell starts to discharge, as in to say the voltage of the cell goes on decreasing. So it starts at a particular point, right? It starts here, and then from there it goes on decreasing because the load is drawing power from the cell, and it goes on decreasing till a certain point, and at this point the load has been switched off. So after this, you will notice a behavior of the cell, okay, which I am now like I'll be just highlighting this. Okay. So here in this portion, you will notice that the voltage is once again beginning to rise. So this portion is measured immediately, or you can say just within a very short few seconds or minutes after the load is released. Okay. So this portion is what is called as transient voltage. Transient voltage. Okay. So in like simple explanation, it is basically the voltage that is trying to return to its steady state value after the load has been released. Okay, so this portion is not exactly open circuit voltage. It is called as transient voltage. Means that this cell is still trying to achieve the steady state voltage. So we will see that in the next slide, how exactly that looks like. Okay, so this is basically an inherent characteristic of every lithium ion cell that you will come across, whether it's of NMC type or LFP or NCA or any type of lithium ion chemistry you take, if you apply a load and then you remove the load, you will notice that the voltage will behave like this every time the load has been removed. Okay. So this is, in other terms, it is also called as relaxation. Okay. So the voltage is trying to once again achieve the true OCV, or you can say the steady state value. So we will understand that in the next slide. So the same case here, I'm elaborating this as case 2, where the cell voltage response is observed once the cell has been rested, or you can say relaxed, for 1 hour after the load has been switched off. Okay, so in this case, you can see the graph has been extended. So we start with turning the load on. Again, here the same thing, the voltage drops to a certain point, and then at this point, the voltage has been turned off. And then here in this entire region, you can notice that the cell voltage has risen to certain point, it has increased again to some point, and then it has become steady state. So if I am marking the steady state region, it looks something like this. Okay, so only when the cell achieves this steady state value, or you can say a state where the cell no longer encounters variations like this. Okay, so if you observe in this particular region, you will notice that the cell will have like variations like this, and then it slowly starts to settle down. So the moment it starts to settle down and becomes flat or nearly flat, and where the variations achieve a very small value, as we had seen in the initial slide where it said less than 4 microvolts per second, in that case you can say that at that you can define that at that point the cell has achieved true open circuit voltage value. Okay, so this is why we say that the cell voltage in terms of open circuit has to be measured when it is in steady state. So uh, this value of 1 hour is minimum, so meaning to say it has to be minimum rested for 1 hour to observe some steady state values. So what exactly do I mean by steady state is that, let's say that I consider this entire voltage region, this only this, which is like again under relaxation. So at some point, you will notice that the voltage values start to become repetitive. Okay, at this point, from here onwards till about roughly here, you will notice that the voltage value is increasing. But from here to here, you will notice that they pretty much become constant or near constant. So it's, you can see here like this is near 4.02, this value is near 4.02, and if I were to like switch off or drop the load, this will go on increasing till about the value of 4.1, and pretty much from here on till here the value has almost consistently stayed near 4.1, right? So this is what I mean by steady state. This is the value which is nearly constant and pretty much repeats itself for a very long amount of time. So at this point, when it has achieved nearly 1 hour or maybe slightly more than 1 hour of relaxation, it can be called as open circuit voltage. Okay. So how exactly we are going to perform this experiment and how exactly these values are seen, we will see in further section, which is called methods of testing. So we will come there shortly and we will try to understand that. So now we will look at some of the important factors which have to be considered when you are measuring the OCV. So these are the major factors. So at any point in time, at any for any cell or for any battery pack, so these are the four main considerations that have to be taken into account when you are measuring the OCV. Okay, so the temperature, your ambient temperature and the cell temperature, both have to be considered. C rate. So when I talk about C rate, I mean to say either in terms of charging or in discharging. Then in terms of age, so how many cycles, how many charging discharging cycles it has run. So the OCV in a fresh cell is slightly different from that of the OCV when it has covered like say 800 or 1000 cycles. So again, we will see all this and try to understand with respect to graphs. So there are some graphs which I will be exploring, which I will be like explaining in the next slide. And then we come to one uh, like unavoidable factor. It's called as self-discharge. So this self-discharge is something like all cells and all battery packs have this. So no matter what you do or no matter what condition you put the pack in, it will have some amount of self-discharge. It is very less for lithium-ion cells. Yes, it is like around 3 to around 4% per annum. But still, there will be some self-discharge and it will permanently lose some energy no matter what you do. It is not recoverable. So again, we will see this with some graphs. Okay. So this is what we are going to be talking about now. So the factors. So first we'll begin with this one, OCV variation with temperature. Okay. So you can see here there are three situations. One is the OCV that has been measured at 10 degrees, which is very low. OCV that has been measured at 25 degrees, and OCV that has been measured at 40 degrees. So respectively, you can see the legend there, the blue, red, and yellow lines. So here it dictates one important thing, that your temperature variation, that is to say the OCV variation with temperature, is very important. It has to be considered, and especially battery management systems have to know this at all points in time, because according to this, the terminal voltage also will be calibrated. Okay, as in to say, when you're going for estimating the resistances and the terminal voltage, predicting some other values within the BMS, the software program, it has to be calibrated according to the temperature here. Okay, because even the resistances will change. So you can see here at 10 degrees shows higher OCV value compared to that of 40 degrees. So especially if you observe a point after the 60% mark. Okay, so if you consider only this region, you can see that the blue line, that is for 10 degrees, is higher than that of the other ones. The reason for this is because in one of the previous slides, I had talked about this concept called relaxation. In 10 degrees, you will notice that there is little bit of more relaxation and therefore higher measurement of OCV compared to other temperatures. So let me just draw that here. So let me just consider a case where I have discharged the same cell with the same specifications, the same material and the same manufacturing company, you can say, with the same like format and everything. So let's say that I am discharging the cell. It is undergoing the same like the trend like this. Okay, and pretty much the same like relaxation is happening. Same load is being given. Everything is like theoretically, let's say it is all the same. Okay, so this part is the load. In this region, the load has been turned on, and after this, here in this region, the load has been turned off. Okay, so and let's assume that what we are looking at, this is at 25 degrees. Okay, so let's say that this achieves a particular steady state within 1 hour, and then it comes to rest at, as we had seen previously, at some value like 4.1 volts, as an example. Now I'm going to compare this to another temperature, say for example 10 degrees. So for 10 degrees, you will notice that the voltage drop is like this, and then once I let it go, once the voltage starts to relax, it'll relax like this. Okay, and it comes to rest at a slightly higher value. Say as an example, say roughly around 4.02 volts. And this is slightly higher than what we had seen in the 25 degrees example. Okay, so this orange line is at 10 degrees Celsius. Right. So now if you observe at 40 degrees Celsius, you will notice this. So for 40 degrees, it comes like this. And this is where it ends. Okay. So this yellow line, this is at 40 degrees Celsius. So in essence, this is what is happening. So as in when you change the temperature, the voltage behavior changes drastically, and it affects the relaxation, it affects the way in which the cell behaves under load and also outside the load. That is to say, when the load is turned off. So basically, if you repeat the same discharge experiment multiple times, you will notice that your voltage curve also goes on changing, uh, as in when you change the temperature as well. Okay, so this is basically what is happening here, and this is what you're observing in terms of the OCV changing its trend line below the 60% mark. Okay, so this is what is happening here. So then we come to another aspect, OCV variation with respect to age. So we had talked about one of the questions from the poll, which asked like whether OCV has any change with respect to age, or whether it's negligible or not. So there will be some change. It is not as significant as that when you compare it to either C rate or with respect to temperature, but there is still some change, and it has to be once again accounted for once you're going for cell testing and characterization, and then eventually when you're implementing this in the BMS and back level integration, the change in OCE with respect to cycle count also has to be accounted for. Okay, so you can see the two trend lines here. The average cell, which is basically the fresh cell, this green line, this is the fresh cell, and the orange line that you see here, this is the defected cell. Basically, it is the old cell. It has run multiple cycles and it has undergone severe degradation. And then eventually you will notice that as and when you approach relaxation, you will notice that it relaxes much less compared to that of the average, or you can say the fresh cell. You can pretty much make that out when you're comparing it to this region. Again, below the 60% region. So this part. Okay. So this because this portion is so important because this is where majority of the losses happen, and this is where majority of something called as like polarization happens. So this is an entirely like separate study or separate like field of explanation. Polarization comes under basically electrochemical reactions that will cause some losses within the cell, and this region is like the most studied region because that's where the majority of the polarization happens. Okay, so this is just to give you an idea how the um, build up in terms of polarization, build up in terms of resistance causes a change in OCV curve. Okay, so then we have with respect to self discharge. So you can see here um, the y-axis that is being shown here is in terms of capacity, but it also applies to voltage because you will notice that when you store a cell uh, over a very long period of time, you can see here it is crossing 1 year in terms of storage. So when you store them without any activity, the open circuit also trends starts to like drop, or you can say there is some irreversible loss in voltage of the cell. Okay, so if you also change your temperature, so if you have some effect of temperature, say for example you store at 25 and then you store another battery at say 45 or 50 degrees, you will notice that the rate of degradation also changes along with it. So it's very evident over here in this graph, blue versus red line. And even another factor comes into play, that is your SOC, state of charge. So your state of charge is one very important factor. So even that will influence at which at what rate the cell will start to degrade. Okay. So for example, let's say I have stored at very high SOC values, say like greater than 90%. Again, this will cause fast degradation. So rapid degradation. There will be like very fast loss in a loss in voltage, loss in capacity, things like that. But if I store at say near 45 to say like 55%, it is optimal. And if I store at a temperature of roughly around less than 20 degrees, say around 15 degrees, then the rate at which the degradation happens is much lower. So you can expect that the curve comes something like this, which is like say at 15 degrees Celsius. And if I'm having an SOC between 45 to 55, okay. So yes, this is another influencing factor on the OCV. So in this case, it is irreversible loss. So in some of the previous cases, to a certain extent, that you can expect that the voltage will be able to be recovered to some extent. But in this case, no matter what you do, it cannot be recovered. Okay, it is permanent damage, it is permanent loss, and it cannot, no matter what techniques we apply, it is not effective in the fact that it can't be recovered. Okay, so this is OCV variation with respect to self-discharge. Any cell, every type of cell will have this. It is unavoidable. And then we come to the final part, that is with respect to C rate. So again here, C rate is nothing but how much current is being drawn with respect to the capacity of the cell. So if I draw a very high amount of current, you will notice that it relaxes much more. So you can see this yellow line. The yellow line corresponds to higher OCV values compared to 1C or even half C. Okay, so that means I'm drawing relatively smaller current compared to the capacity of the battery pack. So the yellow line means that the cell has again undergone higher and more relaxation. Blue line shows that it has undergone lesser and more smoother relaxation. Okay, so always whenever we want a smooth and accurate and true OCV curve, it's always better to measure it under smaller discharge values. So half C, even smaller sometimes, maybe like less than half C, one third C, or even one fifth of the C, based on that. Okay, so these are how the trend lines can be understood with respect to every single factor. So by understanding these graphs, we'll be able to calibrate any algorithm in any battery management system application, provided that we understand how it changes with respect to all these factors. Okay. So now we come to an important aspect, like how do we get the OCV curves? Like we have seen all these OCV curves, but how do we measure them? How do we get them? So we get them by performing some testing procedures. So there are two methods that I'll be like discussing here. It's up to the engineer or the development group which approach they prefer, which approach is most suitable or most advantageous to them. It's not a hard and fixed rule that anyone has to be chosen. Nothing like that. Anyone can be like preferred. So here we talk method one. So let me just highlight that. So method one is where we will go for what is called as continuous discharge. So continuous discharge, pretty much like it is self-explanatory. It means that the cell is being discharged constantly and continuously at the same current, or basically you can say at the same C rate, at the same temperature, till it achieves the end voltage. So you can, like you can see here, if I just mark it, this value, this value over here, if you just observe, this is the end voltage. Okay, it's also called as the terminal voltage at the point which there will be no further discharge. Okay, so at this point, the all operations will be stopped and the termination of the load will happen. Okay, so at a very small current, this will happen. Okay, so you can see the marking here, C by 20 or C by 30. So those are like very small values of current. Okay, so let's say I take a example of say 3 ampere hour cell. Okay, so if I say C by 30, I mean 3 ampere hours divided by 30. So this is going to give me, so roughly around zero point 0.1 amps. Okay, so if I discharge, uh, as an example, if I take a 3 ampere hour cell and if I discharge it at C by 30 or zero point 0.1 amperes, then I will get a voltage curve that looks like this. And this voltage curve can be considered very close to true OCV. Okay, very close. It's not perfect. It's not 100% the real OCV, but this is one of the simplified methods of testing the OCV of the cell, the voltage profile at very small current. Okay, so if I draw, I say about zero point 0.1 amps, then you can expect that this kind of voltage curve can be approximated to a OCV value, right? So here, how is the voltage values taken? Because like how exactly the voltage value have to be measured? It is measured based on the capacity. Okay, so once the testing is completed, you'll accumulate some capacity at the end. Okay, so throughout the discharge, some ampere hours will be accumulated. Say, for example, 3.2 ampere hours. Okay, so this is just an example value. So every 10% change, 10% change in capacity, we can record the voltage. Okay, so it can be 10%, or it can even be 5% change, or it can even be 2% change. That is like purely, again, it's left to the team, the R&D team, what kind of value they want to choose. So based on how much capacity or how much ampere hours has changed from the start point. Okay, so every, if I want to measure every 10%, then like you can take an interval of every 10%, and then totally we'll get 11 intervals, and totally we'll have 11 different voltage points. So we can, again, we can correlate them to the y-axis value. So every time we have to sort of interpolate. Okay, so if I just draw a y-axis line like this, you'll be able to obtain the voltage values every point. Okay, so this is one way of testing the OCV. So here I have all the values, so on. Okay, so this is using continuous constant current discharge using a very small current, that is either C by 20 or C by 30. Now, there is another method, and it is basically using what is called as intermittent discharge. So that I will show here, intermittent discharge. Okay. Now, again, here the C rate is still very small, C by 10 or C by 15. You will discharge the cell for a few minutes. Okay. And once that time of discharge is completed, we will allow the cell to rest for up to 2 hours. So I had said earlier, 1 hour is minimum. In this case, 2 hours to more than 2 hours is sometimes preferable to get a very close and true accurate value of OCV. Okay. So every time the discharge completes and then goes into resting or relaxation, again the voltage is measured. Okay, so instead of seeing in terms of like AH, here we will see directly, we can see in terms of like how the voltage has been recorded at the end of relaxation. So certain amount of time of relaxation is complete, say for example 2 hours, and then the red dots, you can see the red dots. So these red dots all correspond to the voltage values at the end of relaxation. Okay, so like this you can perform OCV measurement at intermittent discharge rates, basically. Okay, so this will now, again, it will form a line something like this. So this is how the OCV line can be obtained. So this is again not in terms of continuous discharge, but in terms of intermittent discharge. Basically, we are discharging every few minutes and then allowing to rest. So this is one more way of doing it. So these are the two methods. Which method has to be chosen? It's purely left to the designer or the engineer, whoever wishes to perform uh, any type of test. It's up to them. Okay. So once the testing is done, we will obtain curves like this. So already it was shown in the beginning. So again, here we'll have a quick overview of this. So there is one more thing that has been added here, and that is OCV measurement during different cases. So that is during charge case and during discharge case. If you measure OCV using the same test procedures which I have shown you in the past two slides, then you will notice that there is a difference in the open circuit voltage of the cell in terms of charge and in terms of discharge. And this particular phenomenon is called as hysteresis. Okay, so not to be confused with transformer hysteresis or hysteresis in electronics. They are not the same thing. In this case, hysteresis is purely with respect to the electrochemical behavior. So inside the cell, there are certain reactions that occur at a certain rate during discharge and occur at a slightly different rate during charge, which is why you will notice that during charge you will see that the voltage difference is much more, or you can say the OCV is slightly higher in case of charge than in compared to discharge. Okay, and this bandwidth, right? This gap, this is what is called as hysteresis, voltage hysteresis. Okay, and as and when the cell goes on aging, you have seen already that your OCV will drop. Okay, it becomes more and more. So your hysteresis band or your voltage band that is within that small area, it will go on increasing. Okay, so that is one important study that is performed over a very long period, say about 2000 to about 3000 cycles, and then the change in open circuit voltage during charging and discharging will be continuously logged. Okay, so the importance is that this voltage behavior will greatly affect the estimation of resistance and even the SOH and all those things, which is a big factor in battery management system algorithms. So when we're studying that, there has to be consideration of this as well. So this you can say is kind of another factor which has to be considered. Yeah. So now I have a question to the audience. So far we have studied the voltage curve of an NMC type cell, that is nickel, manganese, and cobalt. Can I apply the same testing procedure and utilize it for an LFP type cell? So I request Sushmita ma'am, please do share the second set of poll questions so that the audience is able to sort of put in their opinions on this. And yeah, so once we are with this, we can wrap this part up and then move on to the hands-on. So you can refer to the voltage curve shown on the screen. Please do look carefully and then answer which chemistry requires more sensitive measurement. So you can just take a look at the screen, what voltage curve is being displayed there, and then you can have a conclusion. Okay. Uh, yeah, once again, I request the participants to fill up the poll. I see that not everyone has answered. Please, I request all to fill in. Okay. Yeah, I am now going to end the poll. Great. Thank you again, all of you, for answering. So, based on what we have seen till now, the one that requires a more sensitive measurement of the OCV curve is lithium iron phosphate cell. Okay, so let's take a look at the voltage curve we have here. So, what is the one thing that we observe here, which is vastly different from NMC, is if you consider an NMC curve, you will notice that NMC has a slope. It looks something like this, but LFP is totally flat, pretty much from the get-go, from the start till almost till the very end. Only after the, say, about 20% SOC or lower than this, you will notice that there is a sharp drop in the voltage. But pretty much till then, it's a flat line. So that is why the answer to that question, which asks which type of chemistry requires more sensitive measurement of voltage, the answer to that is LFP cell. Okay, so in that case, your SOC interval is much higher. So it will be something on the lines of 2% or even less than 2%, sometimes even 1%. Okay, so if we were to analyze how the IFP SOC OCV curve looks like, it looks something like this. Okay, so it is not having the same slope as that of the NMC. Okay, this is just a sample graph. This is not a true and tried and tested graph. For this, we require much higher frequency of recording. Okay, so this linearization that we are seeing here, this is pretty much a problem that will happen if you uh, take it at a much smaller sampling rate. It has to be very high, so it has to be around 1%. Okay, so then we'll notice that this portion is very much smooth like this. Okay, and that is what is preferable. So that is why your LFP demands more sensitive uh, measurement of OCV. Okay, the reason being that your voltage variation within a very large voltage window, SOC window, is very small. Okay, so we come to the last part. So let me just quickly hand over the hands-on exercise that I had just mentioned. So kindly give me a minute. I will share the file. Right. I have forwarded this. Please do confirm upon receiving your file. It has been sent to everyone. Please give me a thumbs up in the box if you have received it. Okay. So the questions are already pretty much in there. If you can see my screen, it's a short exercise. It's pretty simple. All you have to do is plot it versus SOC. So if you take SOC as the x-axis and case one and case two as your y-axis, then you'll be able to like see uh, some few differences. So I request everyone to carry on the short exercise, and then you can come up with your own conclusions and type it up in the chat box. What you feel is the best representation of OCV, and uh, yeah, the second question as well. How many data points do you feel is necessary to get a better OCV curve? Yeah, so you can take just about another 3-4 minutes to answer this. So if anyone has at least finished the NMC part, LFP portion, maybe you can try it out later. So if NMC portion you have come to a conclusion, then feel free to share your opinions onto the chat box. It's open-ended. There is no uh, hard and defined answer for this. So it's up to you. What do you feel? Do you feel is case one better or case two better? It's very clearly, which has been mentioned here. Long relaxation time versus short relaxation time. What do you feel is the best option? So maybe we can have a quick overview here itself. So yeah, the blue line here corresponds to long relaxation time, and the orange line corresponds to shorter relaxation time, which means that between the discharge period and the relaxation period, the time period is very short. Okay. So you can come up with your own conclusions for this graph. What do you feel? And you can type that in the chat box. Feel free to leave your opinions. Okay. So LFP is another experiment you can try on your own. So it also has its own conditions. And what is the number of data points do you feel is necessary to get a better OCV curve? Yep. So with that, pretty much we are at the last topic here. That is the accuracy of the OCV and SOC curve. So here, there are quite a number of factors we have to consider. How accurate is your OCV SOC curve? Some are factors that you cannot do anything about. They are like unavoidable. Some are controllable to some extent. So based on that, you have all these factors here. So sensor faults or sensor errors, there really is nothing much you can do too much about it. It depends upon what kind of equipment you have purchased. Then approach to measuring the OCV. So very clearly, the idea of this hands-on exercise was to give you an idea what is the difference in the approaches. So whether is it okay to have a short relaxation time, or is it long relaxation time, or is it a continuous discharge? That approach is completely left to you. Which value do you feel is the more accurate one? Frequency of data recording. is basically how much data or how much values is being recorded per second. So naturally, you would like to know all the variations as much as possible. So usually you would get comfortable with a value which is less than 1 second. Sorry, one value per second, or maybe even higher than this, where you can go up to 5 or 10 different values per second. In Decibels Lab, we have a machine that can record up to zero point 0.1 seconds. So which means it can record values every zero point 0.1 second. So we have newer cell cycler machines. So they are all of 5 volt, 20 amps, 5 volt, 30 amps. And even we have some battery back testing machines, which can go up to like 40 amps. So yeah, apart from that, there are some conditions like testing conditions that cannot be avoided sometimes. And that has to do with your temperature, the humidity and things like that. Temperature can, to a certain extent, it can be controlled if you have a climate chamber. Uh, Again, here at Decibels, we do have a climate chamber. So in that, we usually conduct experiments after allowing the cell or the battery back to soak for at least up to 1 day, and then we proceed with the testing. Cell chemistry. So again, your accuracy of the OCV-SOC curve is like very much dependent on the cell chemistry. So we talked about LFP versus NMC. We saw that you need much higher accuracy for LFP compared to that of NMC. Then something again which cannot be usually avoided. It is kind of default. That is the full scale accuracy of the testing equipment. So it depends which manufacturer and all you buy it from. So based on that, you get whether it is accurate or not. You will see it during the testing time. Yeah? So these are your factors which have to be looked upon when you're considering the accuracy of the OCV-SOC curve. So usually for NMC, we had seen that around 5% is a good interval. So pretty much any lower is not required. For LFP, it is 1% usually which is preferred. So where we have the complete change in voltage across the whole SOC window. Yep. So with that, we come to the end. So we just look at the applications and then we can move on to the question and answers. So we have the modeling and simulation applications. So currently we have here also at Decibels, we have focused on cell level, module level, and also on the pack level modeling and simulation, where we have tested the OCV of all of these uh, of the cell, of the module, of the pack, everything, and that has been used for predicting the terminal voltage, predicting the cell and pack level temperature, even the internal resistance, internal impedance, mostly. And that is in terms of modeling and simulation because it goes a long way. Because these two applications itself requires very accurate values of OCV. Otherwise, you don't get a correct and true convergence in terms of your simulation results. Then we come to the battery management systems. So where in these algorithms, very simple ones like capacity estimation of the cell or even of the battery pack using the least squares method or a weighted least squares method, they require a good, accurate interpolation of the OCV values. So the more accurate they are, the more accurate is your value of the capacity. Then even extended Kalman filters, so they are more advanced algorithms where SOC, SOH, SOE, all these things depend heavily upon the OCV values. Okay, so your very accurate SOC estimation requires all these considerations, like how accurate is the variation of OCV with respect to temperature or with respect to age, all these things. Then we come to internal resistance estimation. So again, this plays an important role in age estimation, the remaining useful life, and things like that. And then finally, cell balancing. So cell balancing is done in two cases. Either you do it in rest, in idle case, or it's done in charge cases. So even there, the OCV is very important, and it has to be known uh, very correctly. So yeah, with this we come to the conclusion of our webinar today. So I would like to thank all of our participants for joining and then participating in the pools, taking part in the exercise as well.